All right, today we are going over something called complex numbers. And in the past, when we've had to evaluate something like, say, the square root of negative 64, it would give us an error message in our calculator, and that indicates that we did not have a real answer. Well, with complex numbers, we can actually get a tangible answer. Let me introduce the letter I. The letter I stands for imaginary. And I is equal to the square root of negative 1. And another value you need to know is I squared is actually negative 1. So going back to our original problem that we could not get an answer for earlier this semester, earlier this term, um, we can now find the square root of negative 64. What we do is break down negative 64 as 64 times negative 1. The square root of 64 is 8. And the square root of negative 1 is the letter I. So 8i is our answer. Now, the two types of numbers we'll be talking about in this lesson, real numbers we're familiar with, and imaginary numbers is the other major type of number we'll go over today. Let's look at our first example, where you're given the square root of negative 1, and you got to evaluate this. Using our definition, the square root of negative 1 is I. So our final answer is actually negative I. Going back to evaluating square roots with numbers, negative numbers, let's look at this example. We have the square root of negative 17. And we need to write this number below as a product of a real number and imaginary. Negative 17, we can break it down as 17 times negative 1. Now, the 17 is prime. You can't break it down anymore, or break it down at all, period. But we know the square root of negative 1 is I. So an I goes outside the radical, and 17 stays inside the radical. Let's look at another problem. Let's say square root of negative 80. And we need to write this as a product of a real number and I. 80 is not a perfect square root, but one of its factors is. So we can break 80 down as 16 times 5 times negative 1. Because we know the square root of 16 is 4, so that goes outside the radical. And we also know the square root of negative 1 is I, so that also goes outside the radical. And 5 stays under the radical. Let's look at few simple multiplication problems. starting with the square root of -4 times the square root of -16. Now, normally we would multiply the inside numbers, which would be 64, and take the square root of that number. Since we have negative signs, we need to break these down in terms of I. So square root of -4, we can break it down as 4 times -1. The square root of 4 is 2. And the square root of -1 is I. We'll break down 16 in similar fashion. -16 is 16 times -1. The square root of 16 is 4. And the square root of -1 is I. Now, both i's are understood to be to the first power. So we can still use the product rule for exponents by keeping the I and adding the ones together. So this will give us 8i squared. This is not in simplest form because we know I squared is -1. So our final answer is actually -8. Let's look at some other things we can do involving the letter I, namely raising I to various powers. So let's start with I to the 19th power. Actually, let me start with the second example first. I raised to the 42nd power, and we need to evaluate it. The easiest thing to do is divide 42 by 2. And the reason why I'm dividing by 2 is because we know I squared is -1. So we can rewrite 42 as 2 times 21. Now, I squared we know is -1. No calculator is necessary here because you know if you raise a negative number to an odd power, it's still a negative number. So our final answer here is actually -1. Let's go back to the first example. Again, to break down 19, just divide it by 2. Now, what this means is we can break down 19 to start off as I squared raised to the 9th power. And just like with radicals, the remainder tells you how many i's are left over. So we got an extra I out here left over. Replace I squared with its value -1. -1 to the 9th power is still -1 times our I. And our final answer is actually -I. Just like we did with radicals, with complex or imaginary numbers, we're going over each operation. So we'll start with addition and subtraction first. Before we go over the four main operations, MyMathLab will want your answers expressed in what's called standard form. And standard form is just simply plus or minus A plus or minus B times I, in which A represents the real part of your answer and BI represents the imaginary part of your answer. So let's start with an addition problem. And this one has multiple additions. Just like the letter X, the letter I is also considered, you can combine it as a like term. The regular numbers or integers, we'll just combine those as normal. So negative 9 plus 11 is a positive 2. And 2 minus 3 gives us negative 1. Now you combine the i's just like you would x's. We have 1i plus 7i. Remember, you don't add the exponents here. That gives us 8i. And then 8i minus 18i is negative 10i. That's all you're doing with addition and subtraction, you'll see in just a second. You're combining like terms and like i's. Let's look at a subtraction problem. Subtraction problem, we have 17 minus I minus 5 times in parentheses 2i minus 7. Bring down the 17 minus 1i and distribute the negative 5 times everything in the second pair of parentheses. So negative 5 times 2i is negative 10i. And negative 5 times negative 7 is a positive 35. The last step, combine your like terms and make sure your answer is in standard form. So 17 plus 35 is 52. And when we combine the i's, we get negative 11i. Next up, let's look at multiplication. And we'll look at various degrees of multiplication, or various difficulty levels. Let's start with this problem. We have negative 5i times negative 8i. Each I is understood to be to the first power. Because we have a product, we use the product rule. by adding the exponents. So this gives us 40 I squared. And anytime you have I squared in your answer or anywhere in your steps, you must replace I squared with -1. This answer you don't have to put in standard form. It's just -40. Let's look at a FOIL method problem. We have 9 minus 4i times 7 plus 2i. We can use the FOIL method because we still have a binomial times another binomial. So let's write down our letters. Starting with our first terms, 9 times 7, that will give us 63. Our outer terms are 9 times 2i, and that's a positive 18i. Next, I is inner terms. That would be -4i times 7, or -28i. And L represents our last terms. Here, -4i to the first power times 2i to the first power. Excuse me. That will give us -8i squared. Now, there are a couple of things we can do before we get our final answer. First thing, we can combine our outer and inner terms. So 18 minus 28i gives us -10i. And over here with the last term, we can replace I squared with -1. And that gives us a +8. When we combine our integers, our final answer in standard form is 71 minus 10i. Make sure you remember these two values. You'll be using the second one a lot more with your basic 4 operations. Let's look at another multiplication problem. We have the following question. -11 plus 8i times -11 minus 8i. Remember from radical multiplication and division, actually, if you had something similar, had the same terms, but you had an opposite sign in the middle, then one of these is known as a conjugate. Now, if you're multiplying a binomial times its conjugate, you don't have to use the entire FOIL method, because what will happen to the outer and inner terms, they will cancel out. So all you have to do is multiply the first two terms and the last two terms. So our first two terms are negative 11 times itself, which is 121, and multiply our last two terms, 8i times negative 8i, and that gives us negative 64i squared. Let's replace the I squared with its value negative 1. So that gives us 64. The last step, just add 64 to 121. Our final answer to this problem is a positive 185. Again, if you're multiplying a binomial times its conjugate, you just multiply your first terms and your last terms. Reason why is because your outer and inner terms will cancel out. Let's look at division. And just like we did with radical division, we'll look at a couple of problems where the denominator is just a monomial. For example, 13 plus 5i all over I. Recall from radical division, if you had a single term in the denominator, we cannot have a radical in the denominator. The same is true for imaginary numbers. We cannot have imaginary numbers in the denominator. So with a single term, you just simply multiply the top and the bottom by that single term. Now up top, I'll have to distribute that I. So that would be 5i times I, or 5i squared. And then I times 13 gives us a positive 13i. All over I times I, or I squared. Next step, replace each I squared with a negative 1. And we now have negative 5 plus 13i all over negative 1. Simplify by dividing each term in your numerator by negative 1. So negative 5 divided by negative 1 is a positive 5. And positive 13i divided by negative 1 is negative 13i. And our final answer is in standard form. Now, if you work out a question and get something like negative 13i plus 5, just swap the terms around so you can get your answer in the correct standard form. Now, what if we had a binomial with an imaginary part in the denominator? Let's see how we will solve that problem. For example, let's say we have 5 plus 3i all over 7 minus I. Just like you guys did with radical division, we have to multiply the top and the bottom of our fraction by the conjugate of 7 minus I. So the conjugate of 7 minus I is just simply 7 plus I. Now, up top, when you FOIL out everything, you should get 35 plus 26I plus 3I squared. And remember, when you're multiplying a binomial times its conjugate, you just multiply your first terms and your last terms only. So 7 times 7 is 49. And negative I times positive I is negative I squared. Our answer is not in simplest form yet. We need to replace each I squared with its value -1. So over here we have 35 plus 26I. Right here, that would be 3 times -1, or just -3. And just watch your signs here. You already have a negative sign outside. So we have 49 minus a -1. And you guys know that double negative turns into one positive sign. So let's see what we got left. We have 32 plus 26I all over 50. Now, technically, that's not in lowest form, not really in standard form. All you got to do is, because our terms in our numerator have the same common denominator 50, then we can split our answer into two separate fractions. So up here we have 32 over 50 plus 26I over 50. And simplify each fraction by dividing each number by 2. So our final answer in standard form now is 16 over 25 plus 13I over 25. This concludes lesson 25 on complex numbers. This video will be shared later in Blackboard under the announcements page.